All right. So this is the code we are looking at from yesterday. To start with, like I just would like to review this code and fix some minor performance things and try to get a better clarity overall so that so some of you who have some confusion in mind, it will be clarified. I would like to say, so this code is very important because linked list is a very basic data structure. If you are able to code it, then in terms of how to realize a dynamic data structure such as linked list or any other thing, once you learn, then anything else you encounter in your data structures course, you will be able to handle. Even if it is a bit complex, theoretically you understand what the data structure is, but when it comes to coding, you will be able to do it without much of an issue. Okay, so now let's see the story. We have from line number 4 to line number 8, we defined the structure of a node. If we define the structure of a node, it's a new data type that we have declared. And then on line number 10, we declared a variable called as head. We declared a variable called as head. So there is, I think data structures course is there for EC students also, I think so, for all EC students. So this is, I put a vertical bar here, right? So this is the data part and this is the link part. The second part is the link next. And what does head contain? What does the variable head contain? This is our head. What does head contain? Head contains the address of the first. Yes. So head contains the address of the first structure. Head contains the address of the first structure. And then, so on line number 12 to 15, we are allocating, we have a function called as allocate node. We have a function called as allocate node. And this function is allocate memory for a single node. And today we would like to slightly modify this node allocate node function. It takes key as a parameter, and what it does is node star n, and n is equal to this. Okay, so what happens, allocate node, it will get a chunk of memory from the heap and it initializes that node with the key value, and the next pointer is set to null, because right now it's like a new baby is created or new node is created and it's not yet integrated into the society. We are not adding it to the end, Anaika. We will see what happens. Now we created a node. At this point, we don't know what happens to the node, where in the list it will be placed. So we are giving it its data and we are saying, next is equal to null. Next field is set to null. And the important thing here is, remember that the lifetime of memory allocated, it is a good, we don't need to do it. If you don't do it here, you have to do it somewhere else, but it's a good idea to do it. Okay, so this is an invariant. The invariant that, when we write programs, we can write programs using invariants. The invariant that we have is, the node that is returned whatever it is, invariant, we put it simply, the invariant that we assure is next is equal to null. If so, it is a good thing. It's a good thing. So people who want to use allocate node in their programming, they can, if this is respected, then they can write their programs accordingly. The rest of the code. So now, for the time being, it's nothing. You don't have right now. You don't know where in the linked list the node will be presented. So you just make it null, okay? Or you can leave it, but keep making it equal to null is good. No, Anusha, just follow my line of thinking. Yeah, all your answers will be cleared. All your questions will be cleared. All we are trying to do is, when we are creating a node, why is it a good practice? Though you will see why it's a good practice. You learn with experience. Key is not the position. Key is your Aadhaar card number or your roll number is the key. Based on, since we are maintaining the linked list in a sorted order, so key will determine where in the sorted list it will be inserted. Okay, are you with me here? Line 19 is very simple. When we are creating a new node, we just want it to be very clean. Our data structure, that the node that we have created, it's like we are wiping its face, sprucing it up like that. Whatever the data that is there, we fill it in. Right now, what we know is the key value, so that much we fill it in. Key is not one element of the list. Key is just a field in the structure. Okay. Are you all with me on allocate node function? I mean, it's nothing. We are just allocating memory for a node, and when we want to insert a new student record or something new with student with roll number, we want to first create a node for him. And when we are creating a node for him, we are initializing the key value. That's all. Okay. Are you with me? Yes or no? How many of you understood, at least to some extent? Key is a field, and we are trying to maintain. Key is just a name. Understood a little. What is there to understand here? This is let's say you're maintaining a list of students, and roll number for every student have a unique key, unique name. So key, you can think of it as a roll number for the student. That's all. It can be roll number, it can be Aadhaar card ID, or it can be something else. Down the lane, so the homework that I gave for section A students is, I would like, instead of key, the name. Okay. Oh, with key from cryptography. Oh, is it? Is it the case? See, usually in databases, there is key is just a name. You can call it as roll number, or it's a unique identifier. Okay. So now on line number 25 to 28, we have free node function. So you give an address, the associated node will be freed. The memory associated with that particular address, it will be freed. So now let's try to look at, so one thing, the search node function, it is very simple. So what I would like you to understand here is when we look at the search node function from line 60 to line 67, so we are having this thing called as a C node. Let's use this. Okay, so this is, that's true. We are sorting according to the roll number. Yeah. So this is C node. So C node initially starts with, we are looking at the search node. C node initially starts with the head. And then, so this is, and then after that, C node is equal to C node next. And then it visits this one, and then it visits this one, and then it visits this one. Okay, 1, 2, 3, 4. So finally, when it, and this is null. Remember, so this is null. Okay, so finally, when we try to go from C node to C node next, it becomes equal to null, and we terminate our thing. Are you all with me here on what is happening in the search node? And let's say we want to add one more function. Void print list. So here, what do we do? Printf. Does C node also go to head? Why will it go to head? Head is not a node. Head is a pointer. It just contains the address of the first. Head contains the address. The size of the structure, for example, it can be 1000 bytes, but head size will be only 8 bytes because head points to the address of the node. Does it make sense, Apart? Is the print list function okay with you? Does it make sense? Print list function. You're just traversing this linked list, and every time we are printing the key. Okay. So now, yeah, thank you. Let me do one thing also. I will put void here before it complains. So now let's see what do we do. Yeah. So now I would like you to take a look at the delete node function which we have written last time. Those of you who were a bit confused, I would like you to pay attention now. I want to clarify this idea for you again. So let's say we use two variables, C node and C node and P node. P node is previous node, C node is current node. So there are two cases I want you to, there is one problem in this code. Yeah, so before I asked you that question. So there are two cases that I want you to look at here. Case one is when, which I would like to call it as base case. In the base case, P node is equal to null, and C node is pointing to the head. C node is pointing to the head. Are you with me? This is the case where C node is that is the base case, that when we start traversing the list for deleting a node, C node is, that is when we are using 2 fingers, and in the 2 fingers, this is finger 1 and this is finger 2. First finger, C node is pointing to the first node in the data structure, and P node is a null. Are you with me? That's the base case before we start traversing the linker list. Because there is no previous node for head, right? So because of that, the P node will be equal to null. The second case is the inductive case. The inductive case is like when C node is pointing to this and P node is pointing to this. This is the inductive case. So this is case 2, inductive case. Now, having seen the base case and the inductive case, do you see, is there any problem in the code that you have written for the delete node function? Is there any problem? There is no correctness problem, but one thing you can see, the code on line 47 to 52, it will unnecessarily be checked again and again and again. The base case occurs only once, but unnecessarily we are checking every time if it's a base case or not. It's a waste of program execution time, right? Yes or no? So it's a waste of program execution time because unnecessarily we are checking every time if it's a base case or not. So what we would like to do is we would like to separate out the base case. Okay, how do we know if it's a base case or not? So let's use a prev node. I will use P node for it. Okay, so what do? We check if P node is equal to null, then we are 100% sure it's a base case. Okay, we are 100% sure it's a base case. And now if that is the case, what we do? We see if C node key is equal to null or not. Okay, sorry, C node key is equal to key. And not only that, if the list is empty, then we will get into trouble. So we want to check if C node is not equal to null first. And this, and C node is equal to. So actually we can do one thing. So this is a slight, before we look at the base case, we look at the base case -1 case. What is base case -1 case? What is the base case -1 case? If list is empty, return. We can use if head is equal to null, but even you can just write if head, it will still work. So Sardak, so anyway, let's use this one. Head is equal to null. This is, if head is equal to null, we just return. This is the base case -1. And now we are looking at the base case. So the list is not empty. Okay. And we want to check if C node is equal to key. If that is the case, what should we do on line 50? On line 50, what should we do? What is the code that we should be writing on line 50? So if that is, if this is the case, when if we are deleting the first node, so what should we do? We should make head point to this. Head point to I think there could be different ways of writing the code. I just want to split it in this way. We want head point to this, and then we want to free this one. Okay, let me put it So we want to free this node, and then we want to free this. So what should we do here? So let's use green. So this is 1 and this is 2. So we should say head is equal to, thank you Yash, C node next. And then what's the next one after this? Free node C node. Okay, and then clear it. Does it make sense? So is the base case properly handled? Yes or no? The base case is properly handled, right? We haven't declared C node yet. Huh? Okay. Good. Done. So now we would like to go for, let's say on the flip side, if you are trying to delete the node that we are trying to delete, if this is the node that we would like to delete, okay, then what is our strategy? That's the node that we would like to delete. So what we plan to do right now is so we will start with this. P node is equal to C node, and C node is equal to C node next. Okay, and then what we are going to do is C node is good. C node is, yes, C node is equal to it. Thank you. C node next, and someone suggested we can use a while loop. So what we do is we keep traversing this until C node is not equal to null. Does this make sense? And in the code here, in the while loop here, we don't, so this is inductive case. Right now we are writing code for inductive case, which is case 2. Yeah. C node is equal to great. And so this is work. If C node is equal to key, then P node next. Then what happens is P node next. This is P node. So what we would like to do is we would like to take this one. This is 1, and we would like to free this. Okay, and that's all we are doing here. So P node next is C node next, and free C node and then return. That's all. In the base case, P node is always null. No, we want to handle the thing separately, Shivan. The code to handle the way you free the first element versus the way you delete an element in the middle is slightly different. So because of that, we have to handle the base case and inductive case separately. Are you all with me on this one? Delete node code modification, did you understood? Did you understand the delete code modification? Yes, no? So let's say Shiven is talking about, yeah, that's true. On line 49, if P node is equal to null, if C node, I see. Okay. Good point. So anyway, since very good point, we can remove this, because when we start, C node anyway points to head. So we are checking if C node key is equal to key, and thank you, Shivan. Very good point. Does it make sense? On line 49, we don't need to check P node when we start. So we just check if the first node's key is equal to key. And then if that is the case, we delete it and then we return. Otherwise, we enter the inductive case. Again, once more. So are you all with me? How many of you understood it completely? Can I see? I hope you are all with me on this code completely. We are trying to clean up the code that we have written yesterday. That's all we are doing. And I would like you to think about this base case, inductive case business. So that way, there should be clarity of mind. Okay. And your code should not be cryptic as much as possible. So when you start writing programming initially, we think writing cryptic code is cool, but it's not the case. Okay. We have to have very clear clarity of thought, divide it, write the code in such a way so that if someone else reads your code, they will be able to understand. So now let's write the code for insert node. Okay, let's write the code for insert node. So okay, so let's keep the base case and insert. So what we would like to do again is so in the insert node, is there any base minus 1 case in the case of insert node? What is the base case in the case of insert node? Base case is the case when you are trying to insert a key and you are inserting here at the beginning. The key that you want to insert, it is coming up here. It is coming up here. Key is the smallest. That is the base case. Okay. And the inductive case. So let's write code for before base case. Is there any base minus 1 case? Yeah. So the list is empty. Base minus 1 case. So base minus 1 case is the case when the list is empty. That is, if the list is empty, then head is equal to null. If head is equal to null, then what happens? Head is equal to allocate node key. Does this work? Are you with me here? This base minus 1 case, does it make sense? You created a new node and head points to that. Now I have a question for you. If here, if line number 20 is not there, then what should we do here? If line number 20 is not there, then what should we do after line number 36? If we have to make head next is equal to null. Exactly. So this is the reason. So we have to patch up the code. But if you maintain this invariant that, this next is already set to null, then we don't need to do anything about it. Does it now make sense, Aneka? Like why making it next? It's a clean way of doing it. You can do the other way also, but this is one way of. So base minus 1 case is done. Now, can you tell me the code for What is the condition for base case? Under what condition base case will be invoked? Under what condition base case will be invoked? Key is smaller than, so key is smaller than head key. This is the case. It's not when one node is present. It doesn't matter how big the list is. If you are inserting it at the beginning, okay. So if you are inserting it at the beginning, okay, here we are inserting this. This is the one, this is the base case. What is the code for base case? What should we write here in line 44? Line 44, what should I write? MLOC is equal to size of database. Abhinav, you are in out of form today. Actually, we should do one thing. Node star n here, because we want to insert it anyway. So we will do this allocate node business at the beginning itself. And we will just say n. Now tell me the story. So what should we do now? What instruction I should write? Okay. Good. N of next is equal to head. Awesome. And head is equal to n. Return. Cool, huh? That's all. Nice, no? How we are systematically. Now, can we write code for the inductive case? What is the inductive case? The inductive case is when we are inserting a node here, then what happens? Let's use green. So this will point to this, this will point to this. Now, can you tell me the code for inductive case? Oh, for inductive case, we need to have a loop. Huh? Okay. Good. Thank you. No. Yeah, we need to search for it, right? Okay. Oh, we need to search for it first. So we have to do few things here. Node star p node and c node, and where p node is equal to head and c node is equal to head next. Is this a right thing to do before the while loop? Is this a right thing to do? We are placing our, because first node, P node should point to the first node and C node should point to the next node. And we will conclude, we will not proceed. This loop terminates if, while C node is not equal to null, we keep proceeding. So we will write some code here, but that's all right. But at the end, what should we do on line 61? Between 59 and 60, we write some code. What is the code that we should write at the end of the while loop? We have to move our fingers. Remember, we are keeping track of, we are using two fingers. One finger is on the previous node and the second finger is on C node, and we keep moving it to the right. So what do we do? So we write P node is equal to C node and C node is equal to C node next. Awesome. Cool. This is the code for traversal. Nice. So now what is the condition that we have to check? The condition that we have to check is if key is less than C node key, then we have to do some stuff. And after we do some stuff, what do? We return. Are you all with me here? Does the if statement make sense? Because as we keep moving, we are checking whether the key that we would like to insert, whether it is less than the current C node. If that is the case, let's say, am I going too slow for you guys, or you're getting bored, or all right? Let's say you are inserting 75. Then what should we do? So this turns out to be 75 is less than 100. So we want to insert 75 after next. So what should we do? First is P node next. Thank you, Sardak. Sardak is really helping me out today. And after that, what's? Thank you, Ash. N next. See, it's all programming is fun. Huh? This is P node. N next is equal to C node. It's all logical thinking. That's all. This is how we can insert code. That's all. So that's it. So we have written code for the inductive case. So now let's say there is an issue. Let's say if you are trying to insert, this is 200, and if you are trying to insert 300, then 300 is the last element. Okay, 300 is the last element. So we have to insert it at the last. So what is the story here? The story here is, so this 200 should point to this. This is the only thing that we have to do. Okay, so let me say this is the right way to do this. This doesn't work. Okay, so if without having this, let's call it as inductive case plus 1. How do we handle inductive case plus 1? In the case of inductive case plus 1, what will be C node? C node will be equal to null, and P node points to the structure which contains 200. So P node next is equal to N. That's it. Awesome. All good. So we divided it into base minus 1 case, base case, inductive case, and inductive case plus 1. Okay, all happy? Everyone with me here? Okay. So now we will try to write main. Yeah, so FT is equal to F open. Let's say I use keys. Between all of you know how to use files by now, right? Don't we need to do? Yeah, you tell Yash, do we need to do? Do we need to do N next equal to null? Think about it, Yash. Why it's not necessary? Can someone answer? Anika, can you help answer Yash's question? Person D. Yeah, exactly. Okay, so that's it. That's our code. Shall we compile? Okay, let's compile the code. I'll remove all these drawings. DCC insertion. Key undeclared. So I have this file, Control O. Okay, let's create a file keys.txt. Can you type in some random numbers in the chat box so that I'll just use them? -2, 1, 2, 3, 3, 7, 23, 34, 15, 444, 34, -34, 260, 233, 21. Okay, thank you. Good. Great. Code got compiled. And if you run, what do we get? What will be the output? Nothing. So what should we do? Hey, why it didn't give a segmentation fault? Oh, okay. I just used keys.txt. Okay, I see. Argv of 1. Why was it nothing? Because we are just inserting now. We are nothing. It's like we didn't print anything. We already wrote code, na? For once, we already wrote code for print list. See, for section 1, so now when I run it, what will happen now? When we run it, what happens? Earlier, we didn't get anything, seg fault. We'll get seg fault. Because we didn't pass this, we have to pass a command line parameter. Okay. Can't open an empty file, it will give a segmentation. Because we are opening the first argument, command line argument. If you don't give any command line argument, then let's say FP will be equal to null. And when you are try to read from a null stream, then you'll get a segmentation. Okay. So now GDB. I will put a break on line number 139. 139 is the last line here. Run keys.txt. Okay. So now the whole program has executed and we are on line number 139. We stopped. So now we will call print list. Why print list? Oh, okay. See, we are passing key as a parameter which we are not using. So what should we do? We will pass some dummy parameter. Remember, the parameter 10 doesn't have any effect. P stands for print. Okay, did you see the element sorted? Okay. Now tell me an element which you would like to insert. You want to insert 0, huh? insert node. So there are some interesting things happen in the in section A, but it can be anything. It doesn't matter. Minus 34, minus 2, 0. Did 0 got inserted at the right place? So tell me one more number. $87, 100. So let's use a given number where we have to add it at the end. So I will put 5 digits, 6 digits. What is that? Yay, it got added at the end. P, we have to call the function. I don't know how to call the function apart from using the p print the command. If there is any other function, maybe help call. Okay, maybe call will also work. Call insert node. Let's do one thing. Call print list. Yes, call will also work. It's just an expression, print and no. So now shall we insert something less than minus 34, minus 50? Call minus 50. Yay. Okay, so now let's delete 5000. Let's delete 23. Interesting things happen when we deleted delete node. Which one you want to delete? Let's delete 34. 34 got deleted. Now let's delete 5, 3. Okay. Delete a number not present. Huh? Okay, so the code is working, it looks like, but some interesting things happened in section B. I think it's not in the code, but I think some GDB did some mischief, some interesting things happened, but we are not seeing that things happening here for some. Okay, all good. Everyone happy with, you completely understood how things are working. And so one thing I want to share, GDB is very powerful, because in order to test all these things, I've thought of writing a terminal kind of thing here. And if I write a terminal kind of code in main, then I have to parse whether it is an insert instruction or a delete instruction or a search instruction. All those things, it will take quite some time to write that code, to parse that code, and So, and then later I got an idea, hey, why not we just use GDB, and GDB will does everything for us. At least in this case, we are good. Okay. I see only 54 students. Is there, what's going on? I mean, if you're all good and understanding everything, no problem. But Anyway, so those of you who are here, does this make sense? Are you completely with me on the code here? No issues, right? Okay. So we will take this code, and yeah, the homework for you is, I would like you to do line number 6 instead of key, or along with key, I would like you to insert a name. Okay, there are a few interesting challenges you will face there. We looked at them before, it's not like nothing new, but when you do it one more time, those ideas will be reinforced. It's okay, you can sort according to, you can sort according to name. Okay. Lexicographic, yeah. So, yeah, that's all for today. We will take this same code, and in the next class, we would like to see a couple of things. One is how to write, again, convert this into a multi-file program, number one. Number two, how to use makefiles. And we also look at what are called as memory leaks, how to analyze memory leaks using Valgrind. Not at binary trees. I think binary trees, etc., you will learn in data structures. Let's not worry about it. Okay. But I would like to introduce more ideas which you may not study in your data structures course. Okay. And yeah, so that's all